Hi, this is Mr. Wartsky, and this is the first screencast of the genetics unit. If you have any questions, feel free to watch the video over again, read the textbook, or maybe ask me tomorrow in class. So let's get started, shall we? Yep, let's do it. So we're going to introduce genetics first with a discussion of the history of genetics. We're going to focus solely on one man, Johann Mendel. That's how he was born. He lived from 1822 and he died in 1884. He was a monk, so that's why they call him Abbot Gregor Johann Mendel, or Mendel. Mendel. He was a sickly child. He had no ambition whatsoever, and he was told by a priest to become a monk. That's how much ambition he did not have. He entered the Augustinian monastery, and he fell in love with teaching biology. He wanted desperately to be a biology teacher, but on his way out to Vienna, on the train ride, he started to worry. And when he got into the examination, the oral part of the examination, he froze. And he could not teach biology. His superiors sent him to the University of Vienna for 2 years, the U of V, where he studied the scientific method. He started to breed plants. He did some physics work with the Doppler, the guy who came up with the Doppler effect, Doppler. And he fell in love with learning. So he got back to his monastery and he started to breed peas. And he just, I guess, on a whim. And he worked with peas. The problem is that peas self-fertilize. So he cut off the male parts and he found dead bees, put sticks through them, and he would pollinate the plants by hand. And he looked at 7 traits. We call them the lucky 7 because they were either on different chromosomes or very far apart on chromosomes. He was very lucky that he chose these 7 and write them down here. And he looked at 2 different types for each trait. So for the seed form, they were either round or wrinkled. The color of the seed was yellow or green. The color of the flowers, purple or white, and all the way down. Now, if you need to have examples of what he actually looked at, right there, we got a nice little diagram for you for the lucky 7 characteristics. You can go back and take or pause this and write down the different characteristics that he studied. So we need to remember that each pea is a baby with a lunch. If planted into the ground, each pea has the potential of being an adult pea plant and having its own kids. So each baby has its own set of genes, has its own set of traits, and each pea will grow up to be an adult and have its own kids. Now, a genotype, we're going to define some terms now. A genotype is a collection of genes, where a phenotype is a collection of traits or visible characteristics. True breeding plants will only have one type of trait. So if you're true breeding round, you'll only have round. If you're true breeding wrinkled, you'll only have wrinkled kids. If you're true breeding green, you'll only have green kids. So Mendel, he crossed a true breeding round with a true breeding wrinkled in the parent generation. So now we got to take a little side note here, in which P1 equals the parental generation and F1 equals the first filial generation, which are the kids of the parent. Hold on for a second. We'll go right here. So we have the P1, which is mom and dad, and they have 2 kids, and this is the F1 generation here. Child 1, child 2, or thing 1, thing 2. Now, child 2 got married and had a child. Now, the child would be part of the second filial generation, or the F2 generation. If this child got married and had a kid, that would be part of the F3 generation, right? So we have P1, F1, and F2. So the F1 generation, after you had the parents of the true breeding round mated with the true breeding wrinkled, had all round peas. Then he came up with the principle of dominance because he was wondering what happened to the wrinkled peas? Where'd they go? He said that the trait that is expressed in the F1 generation is the dominant trait. The trait that is hidden in the F1 generation is the recessive trait. The dominant traits are expressed, recessive traits are hidden in the F1 generation. So this is what he did. P1, round, crossed with round, that's what the X is crossed, and F1, all round plants. So he went and he crossed the F1 round peas together. You can do that with peas. You can cross brothers and sisters. No one looks down upon that. No one frowns upon brothers and sisters mating. So he got 3/4 round and 1/4 wrinkled peas. Now the wrinkles are back. Yay. And he discovered that there were two types of dominant peas. The homozygous peas they have only one type of plant. So if you're homozygous round, you only had round peas. The heterozygous round plants, or the heterozygous plants, they can have both types of plants. They can have round and wrinkled. So if you're heterozygous round, you can have round babies and you can have wrinkled babies, not like the homozygous. So when he looked at the P1 and the F1 round peas, he discovered that the P1s were all homozygous, these are true breeding, and the F1s were all heterozygous because they had a mixture of round and wrinkled peas. So his F1 crossed with F1 and 3/4 round and 1/4 wrinkled, which would mean that the F1 peas were heterozygous because they had two types of peas. So there are some round peas that only have round peas. Those are homozygous. There are some round peas that can have round and wrinkled peas, and those are heterozygous. Now, the wrinkled peas can only have wrinkled peas, so they have to be homozygous. He discovered in the F2 generation that 1/4 of were homozygous round peas, 1/2 were heterozygous round peas, and 1/4 were homozygous wrinkled peas. So they used the algebraic symbols. Don't freak out, they're just letters. Algebraic symbols to represent what was happening. Now you need to know another definition, which is alleles. That does not say allele. It says alleles. Alleles. Now they are different forms of genes for the same trait. So we're going to use two alleles to describe the shape of peas. Big A will be round allele and little a will be the wrinkled allele. They code for the same trait, but they're different forms of genes, different genes. So they are each alleles. So each parent will give one allele to the kid. So each individual will have two alleles for the seed form. So in the P1, we had big A, those are the homozygous round. Crossed with the little a, those are the homozygous wrinkled. And now the P1, the one parent can only give the big A, since they give one gene, and the other parent can only give the little a. So we had heterozygous round peas. So when we cross that, we got the big A come down here, we got the big A from here, we got the big A, little a, we got the big A, little a, and then the little a, little a. So we ended up with 1/4, or 1 out of 4, homozygous round, 2 out of 4, or 1/2 heterozygous, and 1 out of 4 homozygous wrinkled. That's the FOIL method they use, by the way. So all of this, Mendel came up with his first law. Actually, he didn't come up with this law. Other people came up with the law and attributed to him. Was stated that in the formation of gametes, the genes will segregate into separate gametes. So if you have two alleles here, one gamete will receive a big A and the other gamete will receive a big A. If you're a, little a, then one gamete will receive a little a and the second gamete will receive a little a. If you're a big A, little a, one gamete will receive a big A, and the second gamete will receive a little a. Now, the law of segregation brings up two probability rules, which we'll go over right now. Don't forget to write down the law of segregation and the examples. So the first rule of probability is the rule of multiplication, which states that the probability of two individual events happening at the same time is equal to the product of the individual probability. I'll say that one more time. The probability of two individual events happening at the same time is equal to the product of the individual probabilities. Get that down. So if we have two parents, big A, and big A, little a, What's the probability of having a big A child? Well, it's equal to the probability of one parent giving a big A, which is a half, and the other parent giving a big A, which is a half. So it is equal to the product of the individual probabilities. So it'll be 1/2 times 1/2, and that is equal to 1/4. Right? Same thing with the little a. Little a is a half a chance of giving a little a times a half a chance of giving a little a. So that's 1/4. The rule of multiplication. Now, what happens if there's more than one way of getting something? Well, that deals with the rule of addition. So the probability of mutually exclusive events, that means they can't happen at the same time, happening at the same time is equal to the sum of the individual probabilities. So this basically, you can get the same result in more than one way. The same result in more than one way, you add the individual probabilities. Do you have an example? Sure. So if we have parents, again, big A, little a, and big A, little a, what's the probability of having a big A, little a child? Well, there's two different ways of getting big A, little a, right? Mom can give a big A, dad can give a little a, that's 1/2, right? Times 1/2 equals 1/4, half a chance of getting this big A, half a chance of getting that little a. But there's also another way. Mom can give the little a, oh, I hate when I do that, and dad can give the big A right here. So that's also 1/2 times that 1/2, which is 1/4. So the probability of these two events happening is equal to the sum of the individual probabilities, which is 1/4 plus 1/4 equals 1/2. So there's more than one way of getting the result. You add the individual probabilities together. So early in the 20th century, a gentleman by the name of Reginald Punnett came up with graphic organizers to help us calculate the probabilities of the offspring of different crosses. And you know these as Punnett squares. If you say, I love Punnett squares, they are fun to do. I know that. So the reason why they're called Punnett squares is because of Reginald Punnett. He came up with it. So in the Punnett squares, the gamete will go on the top and the side. I put gamete, 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 gamete. Inside the square, we have possible offspring. So if these are the eggs here, egg, egg, this is sperm and a sperm. When this egg and this sperm get together, we have that offspring. When this sperm and this egg get together, we have that possibility. When this egg and this sperm, that's that possibility. When this sperm and this egg get together, that's that possibility. So that's what a Punnett square shows. Those are the possible offspring from that cross. We can get ratios. So you need the parent gametes to show the possible offspring. So if we have big A, mom, big A, dad, right? So we have, this is one gamete, this is the other gamete, 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 big A, big A, big A, little a, big A, little a, little a, little a. Isn't that so much easier? I know. So we're going to stop here, and we will start with Mendel's second law, which is the law of independent assortment, in the next screencast. I know you're looking forward to it. Have a good night.